Thank you everybody that has come today. Today is the last talk of 4 conversations. After this we will elect our new OBs. So today's talk will be given by Prakash. He worked in ISL Bhopal in hydrology. And let him start now.
Good evening everyone. This is going to be the last talk of the student talk series conducted by the General Club. My name is Prakash, Deori. I worked in ISL Bhopal during my summer internship, and today I am going to talk about the work which I did in my summer internship at ISL Bhopal. The title of the talk is Estimating the Future Water Change and Citizen InVEST. So before I talk further on this topic, or before I start explaining what I did in my internship, let us ask the question to ourselves. Why do we do it? So what's the motivation of our research? So what's the necessity of our research? What impact will it have of our work which we did? And throughout this talk, I'll try to answer this question, or I'll try to explain you why do we do what we do. So we have to start. Let's start from climate change. We all know what climate change is. So we have all heard about climate change in the internet. We have all heard about climate change in news and in textbooks. But as a earth scientist, how do we understand climate change? Climate change refers to the long-term shift in temperature and weather patterns largely driven by human activities and anthropogenic impacts. Now, what are these human activities? These human activities includes emission of CO2, emission of aerosols, deforestation, overbuilding, and much more activities which affects the temperature and weather patterns of the Earth. Now, and what are the impacts of climate change? As we can see, there is melting of glaciers, there are flood events, and again global warming, or the rise in the temperature of the Earth. So we know and we understand what climate change is, but as an individual or as a government, what actually has been done to actually curb the effect of climate change, or what are the steps which have been taken by the government to actually limit or reduce the effect of climate change. So it's important for us to know, as climate change indirectly or directly affects our health. As we know that due to climate change there will be more of extreme weather events such as cyclones, droughts, and wildfires, and there will be also increase in temperature, global temperature, as in the near future. And what actually is government doing? So G20 summit. So G20 summit is G20 or group of 20 is an intergovernmental forum comprising of 19 sovereign states, the European Union, and the African Union. So we can understand that the government takes climate change as a serious topic, and government wants to actually come up with viable solutions to counter climate change. As what they do in this summit is that the world leaders come and meet in a place annually, and they talk about global economy, financial stability, sustainable development, and one of the interesting facts they talk about is climate change mitigation. That how can we reduce the effect of human impacts on climate change. What we will mostly focus on our study is the precipitation because of which how climate change affects precipitation. As we know that climate change is something which affects the weather patterns of the globe. So it is obvious that it will some way, one way or another affect. It will one way or another affect the precipitation. So as you know, the JJAS, which is June, July, August, September, are known as the monsoon period, and most of the rainfall occurs in this June, July, August, September. But due to climate change, what actually is been happening is the extent of this rainfall is been shortened. So we will see a higher amount of rainfall in a very short period of time, which will lead to flood, and we will see a very scarce amount of rainfall where in the winter seasons where we will observe droughts. IPCC. So IPCC is the intergovernmental panel on climate change. It is an organization which is under UN, which works constantly on climate change and science related to climate change. What are the development or what is the policy changes we can do to counter climate change or solutions so that we can somewhat lessen the we can somewhat reduce the climate change. Now, I guess now as I have talked about climate change, we have now understood the why part of this, question. Why we do it? We do it because we have to find some better solutions to actually lessen the impact of human activities on the climate. And we need to, and because climate change will one way or another, it will affect in our lives. And what we do, that I am going to talk in a few minutes. So, and what we do, we estimate the future water yield change in the activity which we invest in. So our study area is the MP region, Madhya Pradesh state of India, which is located in central India, which comprised of 10 rivers, 6 majors and 4 minor rivers. Now the six major rivers which flows through the MP region are Narmada, Tapti, Chambal, Beto, Mahisan, and the 4 minor rivers are Ken, Tons, Godavari, and Sindh. The difference or the distinction between them, the major and the minor is based on their catchment area, which is in the MP region. So Narmada, Tapti, Chambal, Beto, and Mahi and Sindh have a very large amount of their very large area of their catchment or basement in the MP region as compared to these 4 rivers. Now there are some facts about the rivers, as Narmada is also known as a lifeline of Madhya Pradesh, as 1,000 kilometers of its total length of 1,300 kilometers lies in Madhya Pradesh. So we can from this values we can estimate that a large catchment area of Narmada lies in the Madhya Pradesh region, which is also seen from this diagram. So this is Narmada flowing from east to west. Now it has Narmada has 41 tributaries and 29 major hydropower plant projects. Now this 29 major hydropower plant projects, this is something we must focus on. If we can estimate the water yield in the which is going to be produced in the future in this basin, we will be able to estimate the amount of energy that will be produced in Narmada basin for the next 10 years or 20 years. And if we can get the estimate of how much energy is being produced in Narmada basin for next 20 to 30 years, the next upcoming 20 to 30 years, we will be able to tell government that whether investing in hydropower infrastructure will be profit or it will be a loss. As we know that India has a very coal-based energy source, and most of our energy comes from fossil fuels. So if we could estimate what is going to be the future water need, we will be able to actually estimate how much energy can be extracted or contributed from this hydropower plant rather than taking energy from the coal-based sources. So Chambal is the next largest river in the state, and it's an important tributary of Yamuna, and it has three river valley projects: Ganga Sagar Dam, Jawahar Sagar Dam, and Rana Pratap Sagar Dam. Similarly, Mahi is also a very important river in the NC region, as it have Kalana Dam, Manapuri Dam, and Banswara Dam. So, from this slide, we understand that MP region has a very good infrastructure in hydropower projects. So, estimating the water need or the future water need will help us to actually propose certain projects or certain projects to the government, which will which will actually help us to tackle climate change or some way help us to work on something that will reduce the human impacts on climate change. So before I start talking about the methodology, I want everybody to be aware of what a raster image is, because most of my work actually deals with raster images. So raster is nothing but this pixelated image where each cell contains a particular DNA. Let's say you want to study an area. So we cannot study an area directly. We have to some way digitalize that area. So to digitalize that area, we'll select that area and then we'll divide that area into small individual cells of equal size, and we'll assign a DN value to each cell. Now that DN value can be anything. It could be a temperature, it could be a pressure, it could be precipitation, it could be elevation. So DN value is a very good way of working with if we want to work on a very large area. Now, before I talk about these equations, let me understand how InVEST model actually works using this schematic diagram. So when we talk about a system, we don't care about what's coming from. When we talk about a system, we don't care from where the things are coming into the system and from where the things are going out of the system. What we really care about is that how much amount is coming into the system and how much amount is going out of the system. In this case, the water is being added to the system to precipitation, and that precipitation can be rain, snow, as well as fog. In InVEST model, we usually don't care about fog, or InVEST model actually ignores fog. So the only thing which is left is rain and snow. As we know that MP does not receive any snowfall, so the only precipitation that an MP region receives is through rain. Once the water has entered the system, some of the water will percolate into the ground as groundwater recharge, and that will be marked as a loss from the system. And some of the water will be taken up by the plants and it will be released into the atmosphere through transpiration. And some of the water will get evaporated from the system into the atmosphere through evapotranspiration. Now we usually couple transpiration and evaporation together and turn it as evapotranspiration. And the rest of the water which is retained by the soil or the system is contributed to the water yield. And the water yield is what we are actually interested in. So these are the equations. Let me go through it. So y of x equals to 1 minus actual evapotranspiration divided by precipitation, full bracket, multiplied by precipitation. So the y is actually the water yield, as you can see, and the x is actually the grid size or the cell. So what we are actually doing is that we are calculating the water yield for one particular grid using the precipitation and actual evapotranspiration value of that particular grid. And we do this for all the grids in the area. And once we have calculated it, this total together and we get a total from that particular area or catchment. Now, evapotranspiration, precipitation is something which we can actually measure, as we can put a rain gauge in the field, in the study area of the field, and we can get the amount of precipitation that's occurring in that area. But actual evapotranspiration is something which is very hard to calculate. So we use the next equation, that is the ratio between the actual evapotranspiration by the precipitation. And to estimate this ratio, we use potential evapotranspiration and omega. So omega is the empirical parameter, and PET is the potential evapotranspiration. The potential evapotranspiration is the maximum amount of water that can be evaporated from a surface, given that it has an ample amount of water. Now, potential evapotranspiration is then we can calculate it using the coding equation, which is Kc multiplied by Pg naught. So Kc is the LULC parameter. That means that if a land is used for vegetation, but if a land is in vegetation, then it is more likely that it will lose water through evaporation. It will lose water through evaporation. But if we compare it with the barren land, then there is no vegetation in the barren land. So there won't be any much of a loss of water through evaporation, through transpiration, but there will be a loss of water through evaporation. So Kc actually tells us whether the LULC parameter, so it tells whether the land is used for as a grassland, or it's used as an agricultural land, or it's a barren land. And Et is the reference evapotranspiration, which actually gives the corresponding evapotranspiration value for the particular use of the land. Now, omega is the empirical parameter, which is given by ZAWC divided by precipitation plus 1.5. So, AWC is available water content, which is the amount of water which is contained in the soil for the plants to use, and PAWC is the available water content is calculated using root depth multiplied by PAWC, which is plant available water content. So it is the minimum amount of water that needs to be in the soil so that the plants don't die. And in case that particular cell or that field is covered by wetland or water body, we can simply say that actual evapotranspiration is minimum of the value of potential evapotranspiration or precipitation. These are the formulas, or these are the equations based on which the InVEST model actually calculates the volume. So InVEST model is nothing but integrated valuation of processing service and trade-off. So there are a lot of models in this model. As you can see, there is annual water use model, seasonal water use model, crop pollination, crop production. What we used was actually annual water use model. So annual water use model was what actually does is that. It takes the input such as precipitation, plant available water content, reference evapotranspiration as raster files, and then using the following equation, it calculates the water yield which we want, or which we actually is trying, which is actually for our need of, which is actually needed by our research. So now the data collection and data preparation. So to predict the water yield, the future water yield, we need to have the precipitation data, future precipitation data, and the future precipitation data is collected from CMIPC, which is Coupled Model Inlet Computation Project, which actually predicts the future climate, or which predicts the future climate, and it's a very big model, and it has a lot of variables, and so from this model we actually took the precipitation data which this model predicted for the future, which is from 1992 to 2100 actually. So 126 have different scenarios. What we were interested for our study, we took the scenario SSP 126 and SSP 245. So these scenarios actually assume certain things when they calculate or they predict the future climate. So SSP 126 predicts or it assumes a very optimistic approach where government takes necessary changes to reduce the climate change, and it assumes that the carbon emissions will decrease as the time as the in the coming decades. So SSP 126 is a very optimistic model, while SSP 245 is a model which assumes that there is no much change in the government policies and things are left at least as now, and the carbon emissions will and it assumes that the carbon emissions will rise till 2015 and it will start decreasing after 2015. So yeah, the next scenario. So the precipitation data provided by the CMIPC is in format of net CDL. The net CDL is nothing but is a multi-dimensional area data. So it has layers and layers of data compressed in it, and you need to extract from it. So my job in my internship was actually to get this net CDL files from the model and convert it into raster files. So it's not something like when you convert a net CDL file to raster file, it's not a simple task. You need to do a lot of so you need to I have to write a lot of codes to actually convert the net CDL file to raster file. Once the raster file is made, it looks something like this. So this is a raster file of the precipitation data of the MP region. So when we are going to predict when we are going to predict or estimate the future water need, we need a baseline or something from which we will compare the future water need. So for this we took the period 2005 to 2014 as our baseline period, and with respect to it, we are going to estimate whether the future water need has increased or decreased. As you can see, the y-axis gives us the values of the latitude, and the x-axis gives us the values of the longitude, and the color bar gives us the mean daily mean precipitation in millimeters. And these are the precipitation data of different models for period 2021 to 31. This is for the SSP model from period 2021 to 41. This is for the SSP model 245 from 2021 to 31, and this is for the period 2031 to 40. So once these raster files have been generated, what the task which we so after this raster file has been generated, what we did was we load these files in the InVEST model, and then InVEST model kind of calculated the water needs for us, so we didn't have to make out one model. So you can consider InVEST as some kind of black box where you give an input and it gives you output. Only the thing is that I told you what the mathematics or what the equations it uses. So after investing, so let's go to the data and conclusion. So as you can see, these are the names of the different and this is for the SSP 126 for the period 21 to 30, and you can see the relative differences. So as you can see, there is in some cases we can see that there is a decrease in water rate, while in some cases we can see there is an increase in water rate. So there is some kind of increase and decrease of trend in for SSP 126 model from 2021 to 30. And similarly, this is for SSP model CMIPC scenario SSP 126. So this is for the period 31 to 40, and these are the values. As you can see that there is a relative increase as compared to 21 and 30. So this is for SSP 245 from 21 to 30, and as you can see there is a similar rate of increase, while in Marquis there is a 4.2% of decrease SSP 126 and 245 for period 31 to 40, we can clearly see that there is more water related, or there is a higher relative difference of water related in SSP 126 model, which implies that if government makes necessary changes or government makes new policy changes, then there is a chance that the water level in the MP region increase in the near future. Now this suggests us that investing more on hydropower plant projects will help us shift our energy source based from coal power plant to actually hydropower plant, and which will again act as a positive feedback loop and decrease the carbon emission or reduce the carbon emission which is produced by these coal power plants. So this is the representation, the visualization of the same thing as it's shown in the table, and this is the conclusion as there is an increasing trend in both scenarios of SSP 126 and 245. There is an increasing trend in both scenarios from period 31 to 40, while there is more water in SSP 126 and SSP 45. So finally the vote of thanks. So I like to thank my lab members, the URH lab members with whom I work in the summer internship, and to my supervisor, Dr. Sanjeev Kumar Jha, for giving me an opportunity to work with them, and finally to the general club for giving this opportunity to present my work in which I have done my internship. And thank you.
Actually, why the groundwater delivery charge is a loss, is why it's considered.
So it's very hard to actually, you cannot actually know how much water is getting percolated in groundwater.
But